Hello again, everybody. This is our video solution to problem 5 from the fall 2021 Math 302 final at Cal State Fullerton. Let's see, we have a commutative ring R with identity and an ideal A. Oh my goodness, we have lots of questions. So the first question, what are the elements of the quotient ring R modulo A? All right, well that's actually pretty easy to write down. So the elements of our quotient ring, here we'll write R modulo A is equal to, well, you're going to look at the ideal A and then add every element in the ring. Now that's going to give you a lot of redundancy. There's going to be a lot of these that are actually going to be the same thing, but that's okay. Sets don't see duplications. Okay, so that's what our elements look like. They are all, we'll call them R translations of the ideal A. Okay, the next one. What is the multiplicative identity element of R modulo A? So we need something that when we multiply doesn't change which element we're looking at. Okay, these are sometimes called cosets. So this requires us to recall like what the multiplication looks like. So let me just remind you that if I have two such cosets or translations, the product is given by just taking the translation given by the product. So if I want to multiply, say, A plus R by something and just get A plus R out, then I need to multiply R by 1, which means I need to be multiplying A plus R by the coset A plus 1. So the identity, right, this is the multiplicative identity, is A plus 1, where here 1 is the identity of the commutative ring R. Okay, next, show that R mod A is commutative under multiplication. Well, thankfully we've already written down a product in R mod A. Let's write it down in the opposite order. So A plus S times A plus R. This will be A plus S times R. And this is where it's important that we actually had a commutative ring in R, because we know that R times S and S times R are the same thing because R is commutative. So these two elements we get, A plus RS and A plus SR, these are equal because R is commutative. Okay, this is a general thing that happens when we look at quotients. Whatever you had for the original ring, that should hold when you go down to the quotient, not the other way around, of course. Okay, finally, assume that for all x, y, and r, if x, y is in A, then x is in A or y is in A. Prove that R modulo A has no non-zero zero divisors. This is actually just a restatement of something we proved in class, namely, if you had a prime ideal, then the quotient ring is an integral domain. And that's just like you get to see, this first condition is just saying that we have a prime ideal. Well, it's actually a reformulation of our definition of prime ideal, but again, we proved it was equivalent. And then this last bit saying that R modulo A has no non-zero zero divisors, that just means R modulo A is an integral domain. Okay, so we just want to reprove this. Okay, well, this shouldn't be so bad. If I want to prove that R modulo A has no non-zero zero divisors, well, let's assume we have a zero divisor and show that it has to be 0. So let R be an R such that A plus R is a 0 divisor. Notice I'm not going to assume it's a non-zero zero divisor and then get a contradiction or anything like that. I just go straight forward, right? So I'm going to assume that A plus R is a 0 divisor. Okay, what does that mean? Well, that means that there is some non-zero element of R mod A that I can multiply by A plus R and get 0. So there's actually a little bit to unpack there. Okay, so this implies there exists some S in R such that, well, first, I don't want not S to be 0. I mean, that would be bad too, but I don't want the coset A plus S to be 0. Well, what is the 0 in the quotient ring? It's actually anything that would just equal A itself. I mean, you're translating, but you're not leaving A. That is anything where you put A plus an element of A, because A is closed under addition. So what I really want here is S to be in R, but not to be in A. Now this looks really funny because we're doing quotient, so here I'll use the minus sign for now. I mean S is in R, but S is not in A. If S was in A, then its coset will be the 0 coset. So there exists some S in R, not in A, such that A plus R times A plus S is equal to 0. And again, the 0 coset is just A, right? Or we could write it as A plus 0. Okay, so, but I know that the product, A plus R times A plus S, is equal to A plus RS. And if A plus RS is equal to A plus 0, this can only happen if RS is in A. So this implies that RS is in A. Okay, so this is this general statement that we have here, right? If I do alpha plus or A plus X and it's equal to A, this happens if and only if X is an element of A. Okay, but once I know that RS is in A, now I can use the hypothesis. Namely, if I know a product is in A, then one of the factors is in A. So this implies that R is in A or S is in A. Oh, but wait a second. We assumed that S was not in A. So nope, not this one. So that tells you that R is an element of A. But if R is an element of A, then A plus R is just the coset of 0. So then A plus R is equal to A plus 0. And so we actually did start with, we thought we had a 0 divisor, right? But it's actually just 0 itself. So this implies there are no non-zero, right? Where 0, remember, means A plus 0. There are no non-zero 0 divisors in R modulo A. Okay, and that's the end of that proof. Very good. All right, well, we'll see you next time with another problem from this final. Bye-bye, everybody.